Welcome back to the Deep Dive, the place where we take the most complex architectures, the latest enterprise features, and yeah, those hidden security traps, and we distill them into the most actionable, crystal clear knowledge for you.
Today, we are definitely not just skimming the surface. We are undertaking what I think is a crucial mission for anyone managing enterprise infrastructure. We're going to tackle the full stack of modern, high-availability Hyper-V environments.
The full stack. So what does that actually mean?
It means starting from the bare metal fundamentals, the Type 1 hypervisor, and going straight through to clustering with things like storage spaces direct in Windows Server 2025.
Okay, so that's the core infrastructure.
Exactly. Then we integrate the management plane using SCVMM and Azure Arc. And finally, and this is the absolute operational core, we secure the entire data layer using the true power of advanced NTFS permissions.
That is a massive journey. Our goal here is pretty simple. We're cutting through all the internet noise, the outdated guides, the forum sprawl. We want to arm you with the modern, essential best practices and the underlying, the architectural philosophy you need to confidently deploy, scale, and, most importantly, secure massive virtual infrastructure. Think of this as the definitive shortcut to mastering your fabric.
And we see this focus imbalance all the time in the industry. Administrators will spend, say, 90% of their effort on the plumbing, getting the host online, installing the cluster role, configuring the network cards.
The easy stuff.
Right, the mechanical stuff. But if you have perfect plumbing and porous data security, you've completely failed the compliance mission. We have to master the cluster, yes, but mastering the security foundation built on those granular NTFS permissions, well, that's a critical operational imperative in 2025.
Okay, let's unpack this enormous stack. We're going to start right at the bottom, at the silicon level, to understand exactly where Hyper-V lives. So when you install the Hyper-V role on Windows Server, it can sort of feel like you've just installed another application. But the architecture is so much more aggressive, so much more fundamental than that.
It really is.
We're talking about a Type 1 hypervisor, a bare metal piece of kit.
That's right. It's a huge misunderstanding to treat Hyper-V like an application running on Windows. Hyper-V is a Type 1 bare metal hypervisor. The moment you enable that role, the system's entire boot sequence is fundamentally altered.
How so?
The Hyper-V component launches first. It gets in there directly on the physical hardware, securing its position in what is classically known as Ring 1.
Ring 1 sounds cool, but why should an administrator actually care about that specific architectural placement? What's the so what?
You should care because that architecture dictates everything, security and performance. By running in ring number 1, the hypervisor operates in a position of complete privilege, totally isolated from the operating system that runs above it.
Total isolation.
It ensures that the hypervisor is the one responsible for managing CPU and memory virtualization without any interference. It leverages those powerful processor features like Intel VTX and AMD V, along with SLAT, to efficiently slice up physical resources and hand them out to virtual machines. This isolation is your first line of defense.
So if the main OS is compromised,
If the parent partition is compromised, the hypervisor layer is, at least in theory, still safe.
okay, so if the hypervisor launches first and manages all the core resources, what's the point of the Windows OS instance we installed it on? What is the parent partition's role?
Well, that Windows OS instance transitions into what we call the parent partition, and its role becomes highly specialized. It gives up control of the core CPU and memory resources to the hypervisor.
So what's its new job?
Its new job is basically being the dedicated hardware translation layer. See, the hypervisor is too minimal to include all the complex, constantly updated drivers for the huge array of hardware out there, your network cards, storage controllers, GPUs. The parent partition runs all those essential ISV drivers and the management services, like the virtual machine management service and the VM worker processes. It's the only partition that talks directly to the physical hardware drivers.
Okay, but if all the VM traffic has to go through the parent partition to reach those drivers, how is latency not just crippling? That sounds like a massive choke point.
That's the genius of the VM bus. This isn't a physical bus or anything like that. It's a kernel mode, highly optimized in-memory communication channel. You can think of it as being zero latency.
A highway.
It's the high-speed highway between the virtual world and the physical world. Inside the guest virtual machines, you have what are called virtual service consumers, or VSCs. These VSCs communicate seamlessly over the VM bus with the virtual service providers, the VSPs, that live in the parent partition.
And the VSPs do the translation.
The VSPs translate that virtual request into a request for the parent's physical hardware drivers. This VSE-VSP mechanism is exactly why Hyper-V can achieve near-native performance for I/O operations. It completely bypasses slow hardware emulation.
That communication system is absolutely critical. So let's talk about the VMs themselves. Every time we deploy, we face that fork in the road. Generation 1 versus Generation 2. What's the modern, practical deciding factor here?
Honestly, the practical factor is just whether you need to support really old, archaic operating systems. If you don't, you should be using Generation 2 exclusively.
So Gen 1 is just for legacy support.
Pretty much. Gen 1 is BIOS-based. It uses old IDE controllers for booting and legacy network adapters, and it relies on emulation for that compatibility. It's really just a bridge to the past.
And Gen 2, the modern approach.
Gen 2 embraces modern architecture completely. We're talking UEFI booting, which enables critical security features like Secure Boot and a Virtual Trusted Platform module, a VTPM.
And crucially, it uses all synthetic hardware.
Exactly. It boots off a virtual SCSI controller and uses native Hyper-V network adapters. And synthetic just means the virtual hardware is fully understood by the hypervisor from the get-go, which dramatically reduces installation time and boosts both boot and I/O performance.
But this synthetic hardware only works if the guest OS actually knows how to talk to it. And I think that brings us to the core concept of enlightenment.
Precisely. An enlightened operating system. And that's Windows Server 2016 and up, Windows 10 11, and pretty much all modern Linux distributions now.
Thanks to Microsoft submitting that code to the kernel.
Right. It's aware that it is running virtually. So instead of trying to talk to emulated hardware, it uses these specialized synthetic drivers that speak directly to the hypervisor over the VM bus. This full enlightenment avoids the CPU penalty of hardware emulation, and it unlocks all the cool, advanced features.
So if your OS isn't enlightened.
You're just leaving performance on the table. It's a non-negotiable best practice today.
Let's move to the vital task of resource sharing. In really dense environments, we live or die by our ability to manage CPU overcommitment.
Oh, absolutely. Overcommitment is the standard economic model of virtualization. You might allocate, say, 64 vCPUs to your VMs, even though your host only has 16 logical processors.
And that works because you assume most things are idle most of the time.
Exactly. Statistically, you expect the vast majority of workloads to be idle or running way below peak utilization. The hypervisor's job is to manage those physical CPU slices and distribute them fairly.
But when that statistical model fails, when contention suddenly spikes, we need those granular CPU controls. Reserve, limit, and relative weight.
These are your administrative levers to ensure business continuity. Reserve is simple. It's the guaranteed minimum CPU percentage this VM must receive. If you set a 10% reserve, that compute capacity is permanently carved out for it.
And you can't overpromise those reserves.
No, you cannot overcommit the total sum of all reserves beyond the host's physical capacity.
Okay, and limit is the maximum allowed consumption. I love that administrative trick you mentioned with limit. Can you tell us more about the non-burst application of that?
Sure. So limit defines the ceiling. While it's commonly used to prevent a rogue VM from consuming all the resources, the real operational trick is to use it for soft provisioning.
Soft provisioning. How so?
Imagine you provision a new application server with 8 vCPUs. You know you might need that capacity later, but for now, you only want it running at the equivalent of 4 vCTUs, maybe to save on internal licensing costs or just to reduce its operational footprint. You allocate the 8 vCPUs in the settings, but you set the limit to 50%. This artificially caps its usage. When you're ready for the full load, you just increase the limit dynamically to 100%.
Without a reboot.
Without rebooting or reconfiguring the VM at all, it's seamless compute elasticity.
And relative weight. That ensures critical services win the fight when resources get scarce.
Yes. If contention hits, relative weight is the tiebreaker. A domain controller with a weight of 400 is prioritized 4 times higher than, say, a development VM with a weight of 100. The domain controller will always get preferential treatment in the CPU queue, ensuring your core infrastructure stays stable.
Let's talk memory. Dynamic memory is essential for density. How does that memory reclamation process using the balloon driver actually work, and what's the key operational risk administrators have to monitor?
Dynamic memory lets you define a minimum, a maximum, and a buffer, which lets the hypervisor adjust the VM's allocated RAM based on its current demands. The mechanism for reclaiming memory when the host is under pressure is the balloon driver.
Which is inside the guest OS.
Right. It's a kernel mode device driver installed inside the enlightened guest. When the host needs memory, it signals the balloon driver to inflate.
So the balloon driver asks the guest OS for memory pages.
It does more than ask, it compels. The guest OS sees the memory being claimed by the balloon driver as system memory suddenly needed by a device driver, and it must give up those pages.
And if the guest is busy?
If the guest OS is highly utilized, this forced relinquishing means the guest might have to start rapidly swapping active data to its local VHDX paging file to satisfy the demand. Once the balloon driver holds those pages, the hypervisor knows they are safe to reclaim from the host's physical pool.
That sounds like a huge operational risk. If the host gets too aggressive, couldn't the balloon driver inflate so much that the guest OS basically cripples itself with disk swapping?
That is the precise risk you have to monitor. While Hyper-V is designed to manage this carefully, an environment that's grossly overcommitted on memory, especially if the VMs are running memory-intensive workloads that don't respond well to memory pressure, you can see the guest OS performance just plummets.
Because of all that paging activity.
Relentless paging activity? So the actionable insight here is this. Monitor the guest OS page fault rate and its swap file usage, not just the host memory metric. The balloon driver can make the host look perfectly fine while the guest is suffering from terminal latency.
We have the hypervisor tuned and running optimally. Now we need to move to high availability building the cluster using modern features like storage spaces direct.
This is where we transition from just being a host administrator to being a cluster architect. And the prerequisites are crucial. The sources give us a perfect example using a two-node environment configured for Windows Server 2025.
So what are those foundations?
The foundational rule of clustering is consistency. Every node must be identically configured. Same OS and server cores preferred, same patch level, and consistent hardware exposure. The demo used 6 cores and 12 gigs of RAM.
And they have to be on the domain.
Both servers must be domain joined, as clustering requires Active Directory context. And a key point, if you're running this nested, like the demo was, don't forget that required step on the parent physical host. You have to run set VM processor expose virtualization extensions true.
Okay, once those foundational checks pass, what are the mandatory feature sets we need to install?
You have to install the core roles. Hyper-V, obviously failover clustering, data center bridging or DCB, which is essential for converged networks, and QoS, and the file server role, which is actually a prerequisite for storage spaces direct functionality.
Let's zoom in on storage spaces direct, S2D. We're moving away from the old world of external SANs here. How does S2D turn local hard drives into enterprise storage?
S2D is the core of Microsoft's hyper-converged platform. It pools raw local hard drives across all the cluster nodes. The demo used 4 VHDX disks per node, but in the physical world, this would be raw NVMe, SSD, and maybe some HDD capacity.
And the magic is in the software layer.
The magic is in the software-defined storage layer that creates a resilient pool across the network fabric. You just pool the storage, enable it with the Enable Cluster Storage Space direct command, and Windows handles all the distributed data resilience.
Since we are expanding on this, let's get into the hardware reality. What about things like hardware tiering and failure domains?
Excellent point. For production S2D, tiering is absolutely key. The recommended setup usually involves high-speed NVMe or fast SSDs for the cache tier. This handles all the random low-latency reads and writes.
And the big slow disks for capacity.
Right. Larger, slower SSDs or even HDDs form the capacity tier for bulk storage, and S2D automatically manages the data movement between those tiers. Failure domains are just as vital. You need at least 2 nodes for resiliency, but for true protection against simultaneous hardware failures or maintenance, you really want 3 or 4 nodes.
And you have to pick your resiliency model.
You do. You have to choose between a 2-way mirror, where data is written to 2 nodes, a 3-way mirror, data to 3 nodes, or erasure coding, which is more space efficient for cold data. The choice really depends on your node count and performance needs.
Okay, once the hardware and features are ready, we face the challenge of quorum. Why is this cluster voting system so critical?
Quorum exists to prevent the catastrophic split-brain scenario. You can't have nodes losing communication and then both halves of the cluster thinking they are the sole authority.
Because that would corrupt the shared storage.
Instantly. Quorum ensures that the cluster only operates if a majority of votes, that's 50% plus 1, are present. If you lose too many nodes, the cluster gracefully stops all the resources.
And the witness, whether it's a disk, a file share, or a cloud witness, is there to break a tie.
Exactly. For any even-numbered cluster, the witness is absolutely essential. A 2-node cluster has 2 votes. If one node fails, you only have 1 vote left, which is not a majority of 2.
So the cluster goes down.
Right. But by adding a file share witness, like they did in the demo, you get 3 total votes. Now, the surviving node 1 vote plus the witness 1 vote equals 2, which provides the majority needed to stay online. The rule since Windows Server 2012 R2 is clear. The witness only gets a vote if the node count is even.
Before running new cluster, what is the biggest mistake administrators make, and what must they do to avoid it?
They skip or ignore the results of cluster validation. Running test cluster is not optional. It's a non-negotiable best practice. It checks hundreds of configuration points. And if you're using S2D, you must specifically include the S2D tests to confirm the storage configuration is sound.
So a successful report is basically your warranty.
It's your architectural warranty.
What are the common failure points during validation that people often overlook?
Oh, it's often subtle network misconfigurations. The network binding order has to be correct, favoring the cluster and management networks. Another common failure is DNS registration inconsistency or firewall rules blocking specific ports required for cluster communication.
So you can't ignore the warnings.
If the validation tool flags a warning, you need to treat it like an error and fix it. Don't just ignore it, because those warnings often become stability-killing errors when the cluster is under load.
Assuming validation passes, we create the cluster and then provision storage via clustered shared volumes, or CSVs. Why can't a highly available VM just use a standard shared cluster disk?
Because the standard cluster disk model is inherently exclusive. Only one node owns and can write to the disk at any given time. This stops high availability cold.
It can't fail over.
Right. CSVs solve this by presenting a single namespace, that C cluster storage volume X path, that allows all cluster nodes simultaneous, uniform read-write access to the same LUN. This concurrent access is absolutely mandatory for Hyper-V high availability, especially for processes like live migration, where the VM state and its VHDX file are being accessed by two hosts at the same time.
Let's delve into that specific performance nugget you mentioned. The trade-off with the resilient file system, ReFS.
ReFS is fantastic for integrity and scale. It's designed to protect against bit rot and handle massive volumes efficiently. However, if you format your CSV with ReFS, all I/O traffic for that volume is forced into what's called redirected mode.
Redirected mode, what does that mean?
It means the I/O request doesn't travel over the cluster's internal storage path. Instead, it funnels through the coordinator node, the node that technically owns the volume, before it reaches the underlying S2D or SAN storage.
So why does that matter operationally? What's the impact?
If you're running highly intensive workloads, like a large virtual desktop infrastructure farm, a VDI farm, where thousands of users are all accessing a ReFS-formatted CSV, the coordinator node becomes a massive network bottleneck.
Because all the I/O is being funneled to that one server.
All that I/O is redirected over the cluster network to one specific server. The actionable insight here is this. ReFS is excellent for slow-changing backup targets or bulk file storage. But for high-volume random I/O scenarios like VDI, the old NTFS format on a CSV often offers better distributed performance because it avoids that mandatory redirection. It's a key architectural decision.
And finally, the payoff for all this work. Live migration. We can move a running VM without interrupting the service.
Live migration is the cornerstone of proactive host maintenance. It involves copying the VM's actively used memory pages, its CPU state and device state over to the target host. Because that initial copy happens while the VM is still running, the downtime is minimized to only the final transfer of the memory pages that changed during the copy.
We're talking sub-second pauses here.
Sub-second. This capability ensures zero downtime for the guest OS, which lets administrators patch, update, or even decommission physical hosts during business hours.
We have a functioning, highly available cluster. Now we have to tackle the network segmentation and, crucially, how we manage this fabric at scale.
And the network is where old habits die hard. Legacy clusters use dedicated physical NICs for every single traffic type. Management, live migration, cluster heartbeats, maybe ISCSI.
Which uses up a ton of physical ports.
A huge number of ports, increasing cost and complexity.
The sources show the traditional separation, a 192 series subnet for management and a 10 series subnet for live migration. That's fine for simple separation, but the modern consensus is to consolidate using switch-embedded teaming, or SET. Why is SET the best practice today?
SET is the evolution of NIC teaming, built directly into the Hyper-V vSwitch. You take multiple high-speed physical NICs, let's say two 25 gig cards, and you bind them into a single resilient vSwitch. The shift is away from dedicated physical NICs to dedicated virtual NICs, or VNICs, that are carved out of that single massive pool of bandwidth.
And this allows us to manage the bandwidth centrally, which is vital for preventing the cluster from starving itself of resources.
That's the most critical advantage. If you use a single management network for backups, that backup operation can easily consume 90% of the link, leaving insufficient bandwidth for essential cluster heartbeats and, critically, CSV communication.
Which could cause a failover.
It could cause an unnecessary failover. Using SET and VNICs, you can define minimum bandwidth weight values.
How does that weighting work in a real-world contention scenario?
Okay, let's say you have VNICs for management, cluster, and live migration all coming off your shared 50 gig SET switch. You can assign weights like management 5, cluster 20, and live migration 25.
It was a ratio.
It's a ratio. If the total combined load exceeds 100%, the hypervisor guarantees that the cluster VNIC will always receive at least 20% of the available bandwidth, even if the management network is completely saturated by a massive backup. This guarantees quality of service for the infrastructure itself, ensuring that essential cluster traffic and redirected CSV I/O remain responsive.
Scaling beyond 3 or 4 hosts means manually jumping between Hyper-V Manager, Failover Cluster Manager, and PowerShell becomes, well, unsustainable. We need a central nervous system, which is SCVMM.
SCVMM provides that enterprise-grade management layer. It is the single pane of glass dashboard that consolidates all those disparate tools. For organizations with hundreds of VMs and multiple clusters, SCVMM is pretty much essential for operational consistency and efficiency.
What are the SCVMM features that truly justify the complexity and cost of deploying it?
It's really the ability to template and automate deployment at scale. Key features would be virtual machine templates for rapid VM provisioning, the much more powerful service templates, which let you deploy multi-tiered applications, web, app, DB as a single manageable object.
And intelligent placement.
And intelligent placement, which profiles host resource availability and automatically selects the optimal host for a new VM based on current load and requirements. It takes all the guesswork out of resource distribution.
This brings us back to that code versus clicking duality. SCVMM has a great GUI, but experts often insist on using PowerShell.
The GUI is excellent for visualizing the fabric and for one-off tasks. However, PowerShell provides repeatability and consistency. The sources strongly suggest that while you might use the GUI for discovery, you should rely on PowerShell for defining the configuration.
So for things like those SET switches.
Complex elements like those custom SEC vSwitches with specific bandwidth weights must be defined accurately via PowerShell. The key takeaway is that your PowerShell scripts, your new SC virtual machine, your get SC virtual machine, they are your declarative definition of the environment. It ensures that the next cluster you build is exactly the same as the last one.
The hypervisor fabric isn't living in isolation anymore. For true enterprise control, especially in a hybrid world, we need to bridge that gap to the cloud control plane. And this is where Azure Arc-enabled SCVMM comes in.
Azure Arc is Microsoft's technology for extending the Azure management plane to anywhere, and that includes your on-premises Hyper-V environments managed by SCVMM. It works by deploying the Azure Arc Resource Bridge.
What is that?
It's a small virtual appliance that connects your SCVMM management server to Azure.
That resource bridge sounds like the critical point of failure or complexity. What are the operational hurdles involved in getting that bridge up and running?
It is the main architectural hurdle. The resource bridge requires significant prerequisites: a dedicated management cluster, specific network configurations, and often proxy or firewall adjustments to ensure it has continuous connectivity to the Azure APIs.
So you're deploying a whole appliance just for the connection.
You're deploying a highly available appliance just to connect the management layers. The complexity here is high, and it requires planning for maintenance and updates to the appliance itself, not just the VMs it manages.
But once that bridge is established, what's the revolutionary benefit for developers and operations teams?
The benefit is unified governance and self-service. First, it allows developers and application teams to perform self-service VM lifecycle operations directly from the familiar Azure portal start, stop, pause, delete, and create new VMs.
And it's all governed by Azure's security model.
Critically, this access is governed by Azure Rule-Based Access Control, or RBAC. Your on-premises Hyper-V infrastructure now obeys the same security rules as your Azure environment.
And for administrators, how does it help unify security and monitoring?
By using Arc, administrators can deploy the Azure Connected Machine Agent at scale across all those SCVMM-managed VMs. This opens up the entire suite of Azure management services for your hybrid fleet. You can centrally use Microsoft Defender for cloud for unified threat detection, Azure Update Manager for OS patching consistency, and Azure VM Insights for performance monitoring.
So it's a single point of truth.
A single point of truth for security and operations across your entire IT estate, regardless of whether the VM lives in a physical Azure data center or on your Hyper-V cluster floor.
We've established the hardware, the cluster, the network, and the management plane. We are technically sound. Now we pivot to the data security layer. If you get this wrong, all the previous architectural perfection is meaningless. We have to master advanced NTFS permissions.
Absolutely. Compliance and data protection hinge on mastering this layer. Most administrators, they only scratch the surface, dealing with read, write, and full control. But to implement least privilege access correctly, we really need to understand the 13 individual granular rights.
Tell us more about those 13 granular rights and why we should care about moving beyond just using modify.
The 13 granular permissions are the building blocks. For instance, traverse folder execute file lets you navigate without reading the contents, while create files write data is purely for creation. The distinction between the basic permissions is subtle but vital. For example, the modify permission grants read, write, execute, and delete.
But not everything.
But it crucially does not include change permissions or the highly dangerous take ownership.
Why is avoiding full control and preferring modify such a significant security improvement?
Because take ownership is a devastating right. If a user has full control, they can literally seize ownership of a file or folder, grant themselves any permissions they want, and then potentially lock out the original creator or even the administrator.
Wow.
By granting only modify access, you prevent that unauthorized elevation of privilege, and you keep control of the access control list, the ACL, with the administrative teams. This is a foundational step in preventing internal lockouts and maintaining operational control.
Now, for the core principle that causes sleepless nights, deny always trumps allow.
This is the cascading rule of NTFS, and it has to be understood completely. A single deny entry, whether it's applied explicitly to a user or inherited from a group they belong to, will override all allow entries for that user on that specific resource.
So one deny beats 10 allows.
One deny beats 100 allows. If John Smith is a member of domain admins with allowed full control everywhere, but he's also in the temporary group domain contractors, which has an explicit deny on the HR folder, he cannot access the HR folder. The deny wins always.
So manually auditing this is basically an impossibility. We have to rely on the system to calculate effective permissions.
Precisely. The complexity comes from the additive nature of permissions. The effective permission is the sum of allow entries from the user, plus the allow entries from all the groups they belong to, minus any deny entries that apply to them, plus any inheritance from parent folders.
So you can't just look at one folder's permissions.
If you're troubleshooting access, you cannot simply look at one ACL. You have to use the Effective Access tab in the Windows Security Properties or Advanced PowerShell tools to accurately map the result. Relying on visual inspection guarantees errors in complex environments.
Inheritance is designed for scalability. You apply broad permissions high up, and they cascade down. But a lot of admins try to use permission inheritance blocking.
And that's the classic administrative trap. Inheritance is good. Blocking inheritance indiscriminately creates massive ACL sprawl where every single folder ends up with a unique static access control list.
And that becomes impossible to manage.
These unique lists are impossible to manage, audit, and debug. The consensus best practice is to allow inheritance for consistency and just use a strategic, explicit deny entry for the exceptions rather than blocking the entire cascade. Deny entries are much easier to audit and remove when that exception is no longer needed.
Let's discuss access-based enumeration, or ABE. This drastically improves the user experience by making shares look cleaner and more secure, but what's the operational trade-off?
ABE is mandatory for security and user efficiency. Without it, users see every folder on the file share, HR, finance, executive, even if they get an access denied message when they try to open them.
It's noisy.
Very noisy. ABE hides any file or folder from a user who doesn't have any access rights to it. This limits visibility and potential information leakage.
But the performance impact is real, especially on large archival shares.
It is the crucial trade-off. To render the folder list, ABE forces the server to check the permissions for every single object during enumeration before it can list it for the user. On shares that contain millions of files, this introduces significant latency.
So what's the takeaway?
The actionable nugget here is enable ABE strategically on high-sensitivity shares like HR and finance, where security trumps maximum performance. But consider disabling it on vast public archival shares where performance and simple retrieval are the top priority. You also have to be aware that ABE can sometimes interfere with legacy applications or backup systems that need to list directory contents, even if they don't have read access to the data inside.
We talked about the dangers of highly permissive writes, the classic modify everyone mistake. Continuous auditing is essential for compliance and stability. How do we automate this with PowerShell?
Continuous auditing is not a manual checklist. It requires automation. PowerShell is the key tool for identifying weak or misconfigured ACLs at scale. You should have scripts that routinely scan your file system for specific dangerous scenarios, like flagging any share that grants modify or full control to broad groups like everyone or authenticated users. This helps you maintain compliance with frameworks like CIS.
And beyond auditing, PowerShell helps prevent those catastrophic administrative lockouts.
Absolutely. The most common form of accidental lockout happens when administrators use ICLES-inheritance.r to block inheritance without immediately setting new, correct access rules. If you find yourself in that situation, the quickest and safest resolution is to use ICLES-inheritance.e to re-enable inheritance from the parent, restoring access immediately.
Finally, that brilliant solution for temporary access, creating a self-expiring grant.
This is a cornerstone of proactive security and a perfect example of code over clicking. If you have a contractor who needs access to a project folder for precisely 3 days, you grant the necessary permissions using PowerShell, and then immediately after, you register a scheduled task to run a follow-up PowerShell script in 72 hours.
And that second script cleans it up.
That follow-up script automatically revokes or removes the temporary group from the ACL using ICLES remove. This completely eliminates the human error of forgetting to revoke permissions, which is historically a massive source of security vulnerabilities. It's automated least privilege enforcement.
We covered the full life cycle today, moving from the Ring NICUS 1 hypervisor isolation up through the critical data security layer. That's a massive amount of architecture.
We truly did build the modern fabric. We clarified Hyper-V's Type 1 identity, the parent partition's reliance on ISV drivers, and the brilliance of the VM bus. We explored how dynamic memory uses the balloon driver and that crucial operational risk of overinflation.
We architected the highly available cluster, navigating S2D's storage tiers, the quorum mechanism, and that vital architectural decision regarding ReFS on CSVs for high I/O environments.
And we streamlined management, moving to the efficiency of set VNICs with bandwidth guarantees, cementing the need for SCVMM, and understanding how Azure Arc extends the Azure control plane to enable unified governance and self-service, despite the complexity of that resource bridge.
Finally, we secured the data layer with advanced NTFS permissions, learning the crucial difference between modify and full control, understanding why deny is so powerful, and weighing the security benefits against the performance cost of access-based enumeration.
It leaves us with a necessary philosophical question, I think, for any IT professional designing their environment. We spent a lot of time discussing PowerShell automation, its consistency, its ability to manage set switches, its power to enforce temporary security grants and audit weak ACLs. Yet we still rely on advanced graphical tools like SCVMM, Windows Admin Center, and the Azure portal for day-to-day operations.
So where's the line?
Considering the high-stakes nature of the hypervisor and the cluster itself, where is the operational boundary? What critical infrastructure role is so complex or so sensitive that an administrator should always choose to verify via the GUI, even if the underlying task was performed by code?
Think about that as you decide whether to click or code your way through your next cluster upgrade. Thank you for joining us on this definitive deep dive into virtualization and security.
We hope this information helps you secure and scale your environment confidently. We'll see you next time.